All right, shall we get started? More people will show up here in just a minute. Welcome everyone to CC Colloquium for October 27th, 2021. I'm introducing from this slightly different vantage point today to show you that there's no shortage of empty seats here in Marston Theater. So if you haven't been coming in person because you think, it might be like, standing room only, that is not the case. So just want to encourage people, if you are around and want to show up, there's plenty of room. You can spread out. It's no problem. It would be nice to have more people here in person, especially as we are looking ahead. Our speaker next week, Wendy Smythe, is coming to visit in person. We have later November student presentations, CC student presentations, most of which will be here in person, I believe. And at least at the moment, our final speaker for the semester, Gordon Osinski, also plans to be here in person. So it'd be great for those who are colloquium regulars to think about coming here in person as we move into November. Again, there's plenty of room, so there's no worries about being able to do a little social distancing in here if that's what you want to do. With that, I don't think there are any other announcements. So I'm going to turn it over to Karen to introduce our speaker, who provided us with this really cool, moving title slide, which hopefully you guys have not been too mesmerized staring at in the last few minutes. So Karen, it's all yours.
All right, today's colloquium speaker is Professor Jorge Moreno, a professor at Pomona College, also a visiting scholar at Harvard, and a theoretical astrophysics physicist who studies galaxies, including their evolution, interactions, star formation, their place and influence in galaxy clusters, as well as in large-scale structure and cosmology. Professor Moreno has a master's degree from Cinvestav IPN in Mexico and earned a PhD from University of Pennsylvania. In addition to creating beautiful simulations like the one that we see now, and getting the very compelling science results from them, they are an excellent mentor and were awarded Outstanding Research and Professional Mentor by the Society for the Advancement of Chicano, Hispanic, and Native Americans in Science. I have had the opportunity to meet and discuss research with many of their students that they mentor at the annual American Astronomical Society meetings. And Professor Moreno is also active in diversity, equity, and inclusion efforts in the broader astronomy and physics communities. And welcome to CC.
Thank you for a nice introduction. And it's a pleasure to be here. I just want you to, well, please sit in a way that embodies attention and curiosity. And if your mind wanders, just gently bring it back. This colloquium is primarily for students, so there are no dumb questions. If you ask a question, you're doing everybody a service, because it could be the case that half of the students in the audience have exactly the same question. And also even the experts, when you ask a question and the experts hear the speaker give an answer, then they can find newer ways to explain something. So ask as many questions as you can. They're all welcome. And just a little bit about myself. For the last 10, 15 years, I've been working on merging galaxies. So what I do is I take two galaxies in a computer and I smash them against each other. I was on sabbatical last year, so I started thinking about a slightly different topics, and I began focusing on low mass galaxies, how these galaxies evolve in the universe. And this is what this talk is about. But before jumping into the science, I want to acknowledge that I conducted all my work on Tonga Gabrielino land. As an indigenous person myself, it's important for me to make this acknowledgement of land. My roots are Kickapoo in the border of Texas and Mexico, and Zacateco in the central portions of Mexico. Also, I'd like to acknowledge the work done by the people who grow our food, the people who serve our food, the people who clean our offices, because their contribution is fundamental to astronomy. And even though they didn't have the opportunities or the privilege that we have, they are just as curious about the universe as us. So I also like to thank my co-authors. This paper is this work I will talk about today. We submitted this paper to Nature and it's under review. I'll especially like to thank Shani Danieli because she was the one who discovered these dark matter-free galaxies in the real universe. And now this paper is more about simulations. So just a little bit of an outline. This is the plan for today's talk. First, I'll give you a background. This is especially for students and people who don't work with galaxies. So this is a good opportunity to ask questions. Then I'll talk about the discovery of these two dark matter deficient galaxies. I'll talk about challenges faced by other groups. So there's been many papers with simulations like mine where they don't find these objects, and we are the first to actually be able to recreate them. And then I'll talk about the physical mechanisms. How do you create a galaxy without dark matter in a universe that is dominated by dark matter? Something I will do is, because when I'm listening to new information, usually after 10, 15 minutes, my brain stops processing. It's really hard for me to retain more information. So what I'll do is, after each of these sections, I will give you a mini review, and then I will invite questions. And of course, if you're maybe shy and you decide not to ask a question, then you can also ask questions at the end. So hopefully this helps. So let's start with the background. So this is a recreation of the galaxies in a nearby universe. So this is a map of real galaxies with the Sloan Digital Sky Survey. And something you notice is that galaxies come in many shapes. They come in many sizes. They come in many colors. Some of them are blue, some of them are red. Some of them look like footballs or rugby balls. Some of them look like really thin disks, like our own Milky Way. But those aren't the only ways in which galaxies are diverse. Also, you notice that they come in different groups. Some of them are very isolated. Some of them are in groups. Some of them are in massive clusters. And it turns out that the environment they grow up in really shapes the kind of galaxies they become. And it is a lot like people, right? If you grow up in the middle of Kansas, or you grow up in Beijing or Sao Paulo, or like me, Mexico City, your upbringing will be very different. It also, like, for example, you can think yourself when you meet your family. If you have a really large family or a really small family, your interaction will differ. It depends on the size of the system. It depends on who you are, and it depends on how they behave, right? The same is true, for example, if you're a student and you go into a classroom, your identity really matters. How the teacher organizes the classroom really matters, and also how big the classroom really matters. And all those things play a role. The same is true for identity groups, or for example, people who belong to tribes, or people who belong to communities of color, or people who are queer. As we interact with bigger systems like the United States or Mexico or Canada or other colonial powers, our interactions are very different depending on our identity, but also on the country we live in, right? So I want you to keep that idea in mind. But it turns out that this is, what I'm showing you here is this is a real universe. With our telescopes, we can see a stellar light. We can see light in the visible. We can also use other bands, like, for example, radio telescopes, and we can get information like that. But it turns out that the structure of the universe and the dynamics of these galaxies is governed by dark matter, which is something we cannot see directly. So this is an embodied simulation of dark matter. So this is a big chunk of the universe. And we use these kinds of simulations to understand how galaxies evolve. So what people do is they find that galaxies form in this dark matter halo. So each of these bright spots is a dark matter halo. And the dark matter halo, because it dominates the mass budget, and you can think of this as the skeleton of the entire process, right? Even though what we only see is the stars and the gas, most of the gravitational interactions are governed by the dominating mass component, which is the dark matter. So it is now established, for many years, it's been established that most of the mass in the universe is dark matter. But the question is, how do we know that it's there? What do we know about it? So imagine you take a galaxy like this. This is Andromeda. This is our nearest neighbor. How would you measure its mass? So one way is doing it dynamically, right? You see how quickly it's spinning, and then you can measure the mass, and something like this. Now it would take us a long time to wait to actually be able to see this. For example, our own Milky Way, it takes 200 million years to go around. So the last time we were on this side of the galaxy, the dinosaurs were around. So it's not practical to wait, but there are other ways to measure velocities. So we use something called the Doppler effect. So if imagine you see an ambulance, if it's coming towards you, the pitch goes up, but if it's moving away from you, the pitch goes down. So there's something about the way waves travel, that if they're moving towards you, they get compressed and the pitch goes up. And if it's moving away from you, these waves get stretched and the pitch goes down. Light is also a wave. So the same happens. So what happens with the light from a galaxy that's rotating is on one side, you get light that is shifted to the red. So the light is stretched. On the other side, the light is compressed, so it's blue shifted. And this way you can infer that this side is moving towards you and this side is moving away from you. Now, that's not the only information you get from these measurements. You can also do this as a function of distance from the center. So you can measure using this blue shift and red shift effect, you can measure the circular velocity, how quickly the stuff is moving around the galaxy. And just by using Newtonian physics, you can infer the mass contained within that radius. So if you measure the circular velocity and the distance from the center, you can infer how much mass is contained there. And this is a method that Vera Rubin used. So for example, this is a spiral galaxy like our own Milky Way. You can measure how much mass you have in stars within any radius. What you do is you measure how much light you're getting and you convert that to mass. And this curve here describes what you would expect if the galaxy only had stars, right? And if you add gas, it doesn't change that much because there is a very small contribution from gas. But again, this is kind of a theoretical curve. So if you look at the numerator, this goes like square of mass. So as you increase the radius, the mass will increase and eventually will stop and you will get the total mass, right? So it is a monotonic increasing relation. But as you go to larger radii, then this factor kicks in. And that's why you reach a maximum and then it goes down. So by measuring the stellar light, you can estimate the stellar mass. And you would expect that the circular velocity behaves like this curve. But this is what the theory tells us, but this is what the observations tell us. So you can use stars directly, or you can use a 21 centimeter line of gas. And this is what people find. And you see that there is a huge discrepancy. And the only way to bring these two to harmony is to include an extra term, dark matter. And you notice that the larger the radius, the more dominant dark matter becomes. We don't really know what dark matter is. Many people think it's a fundamental particle like the proton, but it's a dark particle that doesn't interact with light, but it's still up in the air. So we would need maybe bigger particle accelerators, bigger colliders to figure out what dark matter actually is. But as astronomers, we know it exists because it interacts with us in a gravitational way. So now not all galaxies are rotation supported. So the Milky Way or any of these galaxies is rotating because it's spinning and the centrifugal force cancels gravity, right? Kind of like when you have maybe you're doing laundry and you have the clothes spinning, but the reason they don't fly off is because you have the washing machine containing them. In the case of a spiral galaxy, stars are spinning very quickly and you would expect them to just fly off, but the reason they are not is because you have mass, and not just the mass from stars and gas, but you have this dark matter halo that is containing them. But not all galaxies are like the Milky Way. Not all galaxies are rotation supported. This is a giant elliptical. This is M87. It has become really famous because it has a supermassive black hole and a jet. But if you also look at dwarf spheroidals, which are really tiny galaxies, they also look like this. So they don't look like thin disks that are rotating. They look like footballs or rugby balls. So, and we call this dispersion supported. The way to think about this is rather than rotation balancing gravity, you can think of a kind of like a mechanical pressure that is keeping them stable. So if you have a rotation supported system, you can use the rotation curves. And if you have a dispersion supported system, this is what you do. So in this case, you have rather than all stars going around in circles, they are going in ellipses in random directions. So you get this ball of stars. So what you do to estimate the mass is the following. Using the Doppler effect, you measure the line of sight velocities, the velocities towards you and away from you. You draw a distribution, you usually get something like a Gaussian. And the width of that distribution, we call that the velocity dispersion. The velocity dispersion is connected to the mass and to the size of the galaxy. This R half means what is the radius that contains half of the stellar mass of the system, right? Then I want you to try to remember this, that there is a connection between the line of sight velocity dispersion, the mass within R half, and the size of the galaxy itself, because we're going to come back to this later. So spiral galaxies, you can determine that they have dark matter, but also with elliptical galaxies like this one, they also have dark matter halos. Now, what happens when you go to low mass galaxies or dwarf galaxies? How does this picture change? So here I'm showing you a spiral galaxy like the Milky Way on the right. And as you go to the left, then you see the Large Magellanic Cloud, and then you see a very tiny dwarf galaxy. And you can look at the star mass. As you go from right to left, the stellar mass goes down. The dark matter also goes down, but the ratio doesn't go down as quickly, right? So the fraction of mass in dark matter actually gets bigger when you have lower and lower mass galaxies. The tinier the galaxy, the larger the dark matter fraction is. They become more dark matter dominated. So you might wonder, why is this happening? Why would that be the case? So I like to make an analogy with coffee. I used to drink coffee. I don't drink it anymore. But when I did, imagine you have a microwave oven and you have two cups. One of them is espresso cup, so it's a tiny cup like this. The other one is a huge mug. You put them in the microwave oven. So what's going to happen is once the temperature goes up, the first one that's going to spill is going to be the little one, because a tiny cup is not able to retain that hot water and it's just going to make a mess, whilst the big one is going to retain it for a long time. So the same is true with dark matter halos. If you're a tiny halo and the gas gets hot for some reason, it will escape very quickly. Whereas a dark matter halo that is massive, it has a really deep potential well. So whatever happens to the gas, it will be more able to retain it. So if you're in a tiny halo and you have a little bit of gas and you're able to make the first star, and that star goes supernova, it will blow out all the gas and you won't have a galaxy left. Now, something that happens very early in the universe, if you go back to the Big Bang, it was this big hot soup. Eventually, the universe became neutral and dark, and it was dark and neutral for some time. And then you create the first stars and the first galaxies. So what happened is, as you create these first generation stars, they send photons all over the universe and they re-ionize the universe. So the entire universe becomes ionized. And what happens to the gas is that the gas becomes a little bit hot, right? So if you have gas that has some temperature, it's harder to keep it in a halo. So tiny halos are not able to capture gas, which is what you need to create stars. So the efficiency of galaxy formation becomes, it goes down as you go to low mass galaxies. Galaxies like the Milky Way are really efficient in turning gas into stars, but the smaller the halo, the harder it is to turn gas into stars, right? So this is a picture from a paper from 2011 where they showed what we call the mass to light ratio. So the mass to light ratio as a function of mass, the Milky Way is around here. And you notice that if you go into the extremely massive galaxies, or if you go into dwarf galaxies, this ratio becomes bigger, meaning that dark matter becomes more and more dominant as you go to smaller and smaller galaxies. So I want you to keep this idea in mind. So before going to the next section, use a mini review. So for rotation-supported galaxies like the Milky Way or Andromeda, we can infer that dark matter exists by measuring the circular velocities, which we measure by using the Doppler effect. And you can do it for dispersion-supported galaxies like elliptical galaxies. What you do is you look at the velocities in the line of sight direction, you make a histogram, you usually get a Gaussian, and the width, we call that the line of sight velocity dispersion. And that is connected to the mass and the size of the system. And we also now know that the smaller the galaxy, the smaller the stellar mass, the more dark matter dominated it becomes. So any questions about this part?
Should feel free to put questions in the Q&A.
Could
Jorge,
someone
can you see the
read?
Q&A?
Could
Can you see
someone
the Q&A?
go ahead?
Yeah, there's one question in the Q&A. Do we know what percentage of the Milky Way consists of dark matter? I see the chart in log form, but what percentage does that shake out to?
So it depends on the radius, but when you go to large radii, it goes about like 10 to 1.
All right, and then another question, in dispersion-supported galaxies, are there more collisions?
So I'm guessing that the question is collisions amongst the stars, right? And
so
the answer is probably, but not really, because the sizes of the stars are negligible relative to the interstellar distances. So even though there are a lot of interactions, the probability of two stars actually colliding is really small.
One additional question, is there only one type of dark matter in the universe?
So we don't really know what dark matter is. Some people believe there are many ideas for what dark matter is. I think the leading idea is that it is a fundamental particle. But there are some ideas of like, well, it could be the case that there is an entire dark sector where you have a variety of particles that have different dark interactions that could do things that are completely different. So I think the model we use is that there is only one type, but it could be the case that there are many types and that they also have interactions that we don't see. And I've even seen wild suggestions where it could be the case that you even have dark chemistry, that you could even make molecules out of dark matter that we wouldn't be able to observe. But who knows? I think it's still up in the air. We only get, as astronomers, we can only see dark matter through gravity.
That's all the questions right now.
All right. So just to remind you, when you go to the low mass regime, galaxies tend to have more dark matter, right? So the next section is galaxies lacking dark matter. So 3 years ago, Shani Danieli and her PhD advisor, Peter Van Dokkum, they found a galaxy. In this group, the NGC 1052 group has a satellite galaxy, a dwarf galaxy called DF2 that doesn't seem to have dark matter. So this is what she found. She measured the line of sight velocity, and she found that it matches the stellar mass. So by measuring how much mass you have in stars and measuring the dynamical mass using the line of sight velocity dispersion, she found that these two agree, which means that there is no room for dark matter. This is challenging in and of itself, but the fact that this is a low mass galaxy makes it even more intriguing, because as I showed you before, dwarf galaxies are expected to be even more dark matter dominated. So she used this instrument called the Dragonfly Telescope. So that's why this is called DF2. And a year later, they found another one in the same group. They found now a second galaxy, DF4, that has the same properties. And these people started to freak out. So there were many papers being written where it says, hey, we need to throw away the standard cold dark matter paradigm. We need to modify gravity, or maybe dark matter itself interacting. And so there was a lot of apprehension because of these discoveries. And I started asking myself, well, maybe I can find him in my simulations. And Shani and I are really good friends. So I showed her some galaxies that I found in my simulations where I made maps of the stellar light and the dark matter. And there were a few of them that you had the galaxy, but it didn't have an associated dark matter halo, which was really weird. And just a recommendation for students, write papers with your friends. It's a lot of fun. So this is Firebox. This is a simulation that me and my collaborators run. So what you do, you simulate a chunk of the universe. We put gas, the gas turns into stars, and there is dark matter. So even though I'm looking for galaxies without dark matter, we're using a simulation that is dominated by dark matter. So let me tell you more about this simulation. So you want to simulate a chunk of the universe. And when you do simulations like this, you call them cosmological simulations, because you want to simulate a large cosmological chunk. And there are two things you want to optimize when you do simulations like this. One, you want to optimize resolution. So the higher the resolution, the better you can resolve galaxies. And you can probe the really low mass regime because you have enough particles to do that. Otherwise, you can only look at massive galaxies. The other thing you want to maximize is the volume of the box. The bigger the box, the more diversity of galaxies you will have, and that will be better. For example, if I was using a tiny box and I simulated this chunk, or I simulated this chunk here, I would get very different things, and neither will be representative. So you want to get a representative chunk of the universe, you want to maximize the box. Now, maximizing the box means you need more particles. And if you have a high resolution simulation, that means that you need more computing power. So these lines tell you how many particles you have, like 500 to the cube or 1,000 to the cube and so forth. And we say that when you maximize both, you increase discovery space. Now, many people focus on zoom simulations of just one system. The zooms are here. So they have really tiny volumes or really high resolutions. There have been many papers recently with cosmological simulations that have really large volumes, like, I don't know, Illustrious or Eagle, and they have really low resolution. And Firebox actually manages to optimize both. And that allows us to discover really cool things. So here I'm showing you the stellar mass on the x-axis and the dark matter mass on the y-axis. Each symbol corresponds to each galaxy in the simulation. And I'm not looking at massive galaxies, so I got it around 10 to the 9. So these are dwarf galaxies. Massive galaxies will be out here, but we're only going to focus on dwarf galaxies because the two dark matter-free galaxies in the real universe are both dwarf galaxies. Now, this is color-coded by the fraction of mass in dark matter. So if this is unity, if you're light lavender, it means that you're dominated by dark matter. And if you're light green, it means that you're dark matter deficient. I'm going to add some lines here. You notice that even though the dark matter mass and the stellar mass are correlated, the slope of this is below unity, which means that as you go to low masses, you become more dark matter dominated. And that's why these symbols are light lavender, whereas these symbols are purple. What about DF2 and DF4? What about the two dark matter deficient galaxies that we observe in the universe? They are down here. So everything above this line is dark matter dominated. Everything below this line is dark matter deficient. So you might be wondering, well, what is going on here? Have we failed? No, because I didn't include all the galaxies. So you notice here in the label, I have centrals, but I haven't talked about satellites yet. So let me talk about that next. So in addition to having a galaxy and a central galaxy and a dark matter halo, galaxies like the Milky Way have satellites orbiting the Milky Way. And each satellite has a subhalo. And there are cases where you can have a satellite of a satellite, and then you will have a sub-subhalo. So the moment you include not just centrals, but also this substructure, this plot becomes this. So the triangles are the satellites. And you notice that the satellites tend to be below this relation for centrals. So being a satellite somehow makes you go down and to the left. If you are a galaxy and you fall into a halo of a bigger galaxy, as you're interacting with that halo, you're gonna lose your mass. Your stars are gonna be stripped. Your dark matter is gonna be stripped. Kind of like when you see a comet coming close to the sun, you see the comet and it has this tail because it's losing material, because it's been tidally stripped by the gravity of the sun. The same is true here. When you have, say, the Milky Way and the Milky Way halo, and a galaxy comes in and becomes a satellite, it will lose gas, it will lose stars, and it will lose dark matter. You notice that most satellites, they lose a lot of stars, but not so much dark matter, right? But there are 7 of them that we find that they actually lose more dark matter than stars. These are the 7 dark matter deficient galaxies. And I named them after the 7 Cherokee tribes because I have indigenous ancestry. I have a friend in Texas who is Cherokee, and he told me about these 7 clans. So I decided to name them in honor of those clans. He consulted with the elders in the tribe, and they said it was okay for me to do this. So I think it's a great naming scheme. So let me introduce you to each of them. And whenever I think about galaxies, I think of them as people. So I feel like each one has its own personality and quirks. So let me introduce you to each of them. So this is Wolf. What you're seeing here is the stellar light. So I'm simulating the light from stars as if you were looking at it with the Hubble Space Telescope. You see that it's very close to a massive galaxy. This galaxy has a lot of blue stars. It has ongoing star formation. And this is Wolf, this tiny galaxy next to it. But if you look at the dark matter distribution, it looks like this. There is no dark matter counterpart. So this is a almost dark matter-free galaxy. In a simulation that is dominated by dark matter, there are some galaxies that don't have dark matter or have very little dark matter. This is wolf. This is wild potato. And this is the dark matter counterpart. This is paint. Notice that paint is a little bit fluffier. And I want you to remember this. This is kind of fluffy. And then you look at the dark matter component and it doesn't have anything. So I have a question for you, especially for students, because this question is going to help us kind of like get clues about the formation physics of these objects. So here's the question. What do these three satellites have in common? So feel free to speak up or put it in the chat. Let's see what ideas you come up with.
You can put it in the chat or the Q&A, and we'll be monitoring that. So can you see the chat, Jorge?
Can you read them to me?
Sure. So one student posts, they look like they're being pulled apart.
Yes.
Another, they're pretty far from the central body. Another, they all look like remnants of when black holes burp. They're almost oriented more linearly than circularly spherically. Tails of light.
Mm-hmm.
They appear on the outer edge of the larger galaxy. They all have satellites. That's it so far.
So all of those are really good ideas. So they are all close to a massive galaxy. They're in the edge, but they're actually really close to the galaxy. They're not like super far away. They seem to be stripped, so they're kind of like spaghettified, kind of like they have these tidal tails because they're being tidally stripped. And something that maybe folks didn't mention is they all are the same color. They look kind of like yellowish. So when you have blue stars, it means that blue stars don't live a long time. So you have blue stars, it means you have ongoing star formation. It's kind of like if you go to a village and it only has puppies, humans, and turtles, and you come 7 years later, you're going to have everything. But if you come, I don't know, 50 years later, all the puppies are going to be gone. And if you come 200 years later, you're only going to have turtles. So here, you only have red stars, which means they are the ones that live the most, which means that they have very old stellar populations. In contrast, the neighbors, they do have ongoing star formation. Another thing you should notice is that it seems like the central galaxy is being perturbed by it. You see that you have this disk, and then you have this kind of like rotated central disk. The same is true here. So it seems that this thing is not only interacting with the bigger galaxy, but it actually plunged through and affected it. And another thing you should notice is that there's only one of these satellites per massive galaxy. You don't have many of them. Now, these are only the first three. We can look at long hair. Long hair is really far away from the central galaxies. And in fact, the central galaxies is two of them that are merging. And what happened here is that long hair actually pierced, it went through the central galaxy. It left the halo. It became something called a backsplash galaxy. So it left the halo momentarily, and now it's on its way back. And this is what the dark matter distribution looks like. Something unrelated to these galaxies, you notice that there are many dark halos that don't have galaxies. And the last three, they're actually in the same group. Bird and blue are interacting with each other. You see that this has these S-shaped tidal tails. And they're really tiny. You see they're really concentrated. This is deer is a little bit farther away, and something you notice is very fluffy. So I want you to remember that deer is really fluffy, whereas these two are really compact. And if we look at the dark matter distribution, it looks like this, basically nothing. So this is going back to our dark matter mass versus stellar mass plot. This is where our 7 galaxies lie. So just to review, there are 2 dark matter deficient galaxies in the real universe, DF2 and DF4, and they are both satellites of the NGC 1052 group. We found 7 dark matter deficient galaxies in my simulation firebox. The satellite, they are all satellites, they all have these tidal tails, and they're all red because they have really old stellar populations. 3 of them are very close to their massive host. One of them is very far away. We call that a backsplash galaxy because it actually left the halo of the host and is coming back. And 3 of them are in the same group. And of all of this, Wolf is the one that is most similar in stellar mass to DF2 and DF4. So any questions about this part?
There's no questions about this yet. There is one other question from the first part that came in late.
Sure.
It's a general question. Why is it so difficult to determine something that constitutes more than 90% of the mass of the universe?
If only we knew. And I think that's like kind of like the $1 million question. Whoever figures out what that is will definitely get the Nobel Prize. It's a question that is being, we're waiting for the answer. Who knows?
Here's another question. So was 7, you've got 7 of these in your simulation, was 7 a surprising number? How many did you expect?
So based on what people have found in other simulations, one would expect none. But when I started looking at the simulation, I didn't design the simulation to simulate these galaxies. I just started making images and they just popped up. And when I told Shani, she told me that's how we discovered the ones in the real universe. We were looking at images and they look weird, and we followed them up and discovered that they were dark matter free. So sometimes that's how science happens. It's just serendipity.
There's another question. Does the fluffiness of the dark matter deficient satellite galaxies appear to change with distance from the galaxy that it orbits?
That is a good question that I don't know the answer to. So that's actually, I never thought about that. That's something I definitely look in the simulation. There could be a correlation between the history of the galaxy and how fluffy it is. I actually don't know the answer to that. Good question.
All right, that's it for questions right now.
All right, so let's move on to the next
one.
one.
I'm sorry, there's questions in the room. I'm sorry, I should be looking back.
Yeah.
I'm sorry.
That's okay.
Hey, does your observational colleague, you kind of alluded to it, and maybe you could say a little more, does your observational colleague have lots and lots and lots of objects in the real data that land exactly on your main kind of, median typical object in your simulation?
So she doesn't, but it's been established already that most galaxies before these 2 galaxies are on that relation.
Yeah. So is there like a possibility that wolf paint and wild potato could have been pushed out by some mechanism from their host?
Pushed out. So because we're able to follow their history, we know that they have been interacting with the host. But there are some ideas of actually when Shani and Peter van Dokkum wrote the observational paper for DF2, one of the ideas they threw around is like, hey, maybe you have a massive elliptical with an active a quasar that pushed some molecular gas and that formed the galaxy. So they claim that that could be a mechanism, but we don't see that in this simulation, at least not at redshift 0. They're all really good questions. Keep them coming.
All right, we got a couple more if you want more.
Sure.
Was there anything else unique about these simulations apart from their good size and great resolution?
Yes, that's a question I got from the referee. And the third thing we do really well is hydrodynamics, so how we model the gas. And we're able to achieve really high gas densities, and which is really useful for modeling star formation. So in observations, there is a correlation between star formation and gas density. And many simulations, what they do, they say, oh, I'm just going to tune my star formation so that it matches that observational fact. And they say, oh, maybe if we make the star formation efficiencies like 5%, it will work. What we do is we say, in our simulation, if a clump of gas is self-gravitating, it will turn into stars at 100% efficiency in one dynamical time. So how do you prevent all the gas from turning into stars? Is because of feedback. So when you make stars, the stars dump light and momentum into the interstellar medium and kind of prevent other regions to collapse into stars. And that way, that relation I told you from observation called the Kennicott law is not an ingredient of the model, but actually it's a prediction of the model. So I guess the third ingredient that makes our simulations unique is that we have a very self-consistent treatment of star formation.
Right. There's one more question. With deer, blue, and bird, do each come from a different galaxy in the interacting group?
So the 3 that share the same They are living the same host. So Deer came from a different direction, and it was also a splashback galaxy. And Blue and Bird, they didn't come in the same group, but they have been interacting. So they were neighbors. They're a lot like this large and small Magellanic Cloud.
Okay, I think that's it for now.
All right. So let's talk about why we hadn't seen this kind of galaxies in other simulations. So challenges faced by our competition or other groups around the world. So here I'm showing you the stellar mass as a function of the ratio of dark matter mass to stellar mass. And the reason I'm plotting this is because I'm trying to compare with this paper by Jackson et al. 2021. This is a group based mostly in the UK and Korea. And they actually wrote a paper back in January. And when they published this, I was like, oh my God, I've been working on this so hard, and they beat me. So I decided, well, to make a plot very similar to theirs. So if this quantity is below unity, means that you're dark matter deficient. And if you're above unity, you're dark matter dominated. Our 7 dark matter efficient galaxies are here. And this is where the galaxies from this Jackson paper are. So they say, oh, for us to be dark matter efficient, you only have to be a factor of 10 to 1. So they find these objects, but they don't find anything here. So it has been a challenge. We believe it's because of our treatment of star formation that we're able to find this, but who knows? Another challenge in the simulations has been to find galaxies with very low velocity dispersions. So if you have recall that if you have a dispersion dominated system, dispersion supported system, that tells you something about how much dynamical mass you have. So DF2 has this really low line of sight velocity dispersion. This is a paper from Sales et al. This is from a different simulation called the Illustrious TNG. And she plots the line of sight velocity dispersion as a function of stellar mass. These are all simulated data points, except the purple ones, which are observations. And if you go down here, you have DF2 and DF4 using different methods, and none of their simulations are able to make galaxies with such low velocity dispersions. And the reason they have low velocity dispersions is because they don't have dark matter. If you have a lot of dark matter, you're going to have a lot of mass, and you're going to have a lot of really high velocity dispersion. In our case, if you look at Wolf, you can measure the line of sight velocity dispersion along any direction. We chose 3 of them, and this is what we get. Especially in the Y direction, you get 7.5, which is really low. And we're the first cosmological simulation to have objects like this. So remember, I told you at the beginning, if you want to know the dynamical mass of a dispersion supported system, you need to know the size and the line of sight velocity dispersion. So here I'm showing you the line of sight velocity dispersion, the size, and these lines tell you the dynamical mass. These are all our satellites in our simulation. This is where DF2 and DF4 live. And this is where our 7 dark matter deficient galaxies are. So you notice that Bird and Blue are tiny, but they have really high, their velocity dispersions are too high. You notice that Deer, Longhair, and Paint, they have low velocity dispersions, but they are really fluffy, especially Deer. But we notice that Wild Potato and Wolf do a good job. And we're the first to be able to do this in a cosmological simulation. So just to summarize, cosmological simulations have struggled to create these kinds of galaxies. And this is the reason why people who don't like the standard model of cold dark matter complain. They say like, hey, your simulations don't create any of this, so maybe we should throw it away. Maybe we should modify gravity or do something entirely different. And the most promising object from this paper by Jackson has 60% more mass in dark matter than the stars. So it doesn't really, they're not really able to recreate galaxies like the ones in the real universe. Well, cosmological simulations have also struggled to create galaxies with really low velocity dispersions. And Wolf is the one that resembles the F2 and the F4 the most when you look at the velocity dispersion versus size plane. Any questions about this part?
So there are a couple of questions, one left over from the it's kind of general.
Sure.
Looking to the far future when Andromeda arrives and begins to merge with the Milky Way, does your model predict what may happen to our satellite galaxies vis-a-vis dark matter?
So when the 2 galaxies merge with one another, you will have a massive elliptical galaxy. and that would affect the satellites in different ways. But we're going to see that in order to become dark matter deficient, something special has to happen. It's not enough just to be a satellite of a massive galaxy. I will show that you actually have to go through that galaxy. So whether or not the remaining satellites have sufficiently radial orbits, we don't know.
And then another question, where is the best location to gather this data? Do you need to be near the equator to gather the initial data?
So the Dragonfly, it really depends on where you're looking. You want to avoid the disk of the galaxy because there is a lot of dust. So you want to look away from the disk of the galaxy. So in a sense, the northern hemisphere is good. But what Shani does is, like with Dragonfly, they look at candidates and then she writes proposals to use something like the Hubble Space Telescope. And she's been assigned, like, I don't know, like 90 hours on the 90 orbits on the Hubble Space Telescope. So to really get down to those details of measuring, say, the line of sight velocity dispersion, you need a space telescope.
All right. Any other questions about this part or in general?
Mm-hmm.
No, none right now.
So let's go to the last part, thinking about what physical mechanisms are responsible for creating this kind of galaxies. So how are these dark matter efficient galaxies created? So we look at Wolf is very close to a massive companion. So it could be the case that you need to be really close to a massive companion, or you have to be interacting with a massive central. So what I'm showing you here is on the x-axis, I'm showing you the stellar mass of the satellite. On the y-axis, I'm showing you the stellar mass of the central. And I notice that my 7 galaxies are around here. I can put the mass of the central galaxy where DF2 and DF4 live. It's right here. And then I can include DF2 and DF4. So all of them seem to be along this line, this 1,000-to-1 ratio. So one of the conditions we need to meet is that the stellar mass ratio between the massive central and the satellite has to be around 1 to 1,000. It cannot be 1 to 10. It could not be 1 to 100,000. It has to be around 1 to 1,000. Now, that's one condition, but also maybe the kind of orbit you have matters, right? So let's look at the evolution of the orbit. So what I'm showing you here is the distance between the satellite and the host as a function of time. It's going from infall to today. When I say infall, I mean the first time it became a satellite. So the galaxy comes in, gets really close, and it goes far away. You have this orbit that is decaying. This gray line is the radius of the host halo of the massive galaxy, and this dotted line is 5% of that. Now we can look at the mass evolution of this object, and it goes like this. These lines represent pericentric passages, and this one represents the pericentric passage when you reach the minimum distance. And you notice that it's more or less decaying, but if I break it into, say, dark matter, it's dropping very quickly at the end. I can look at the stars, and it's even rising for a while, and then it's decreasing slowly. And the gas, it's dropping, and by this time, it's completely stripped. So the gas goes away. You need gas to create new stars, so that's why these galaxies are very old, because they were depleted of gas quite early. Something to notice around this time, the galaxy became dark matter deficient. At this time, the stars dominated over the mass. And then this has increased, right? Another way to look at this is we can measure the fraction of dark matter retained. So this is the mass in dark matter today versus divided by the mass in dark matter when it first fell into the host halo, when it first became a satellite. You can do this for dark matter. You can do it for stars. This is all our satellites in our simulation. And this is color-coded by the time it fell in. So if it's really blue, it means that it was accreted recently. If it's very red, it means that it became a satellite a long time ago. And this is where our 7 galaxies lie. Yes, they lost a lot of stars, but they lost way more dark matter than stars. For example, paint, for every mass in stars that it lost about maybe 1,000 times more in dark matter. So there is a mechanism that is stripping you a little bit of stars, but it's stripping you a lot of dark matter, making you dark matter deficient. And if we look at the orbit again, we notice that especially when you go below 5% of the radius of the host halo, that's when you become dark matter deficient. It seems that, for example, this interaction here, you didn't go within 5%, so nothing much happened, but this one here and this one here and so forth, they went well inside the host halo. And actually that 5% is roughly the size of the stellar component of the central. So what is this telling you is for you to become a dark matter deficient galaxy, not only should you be a satellite, but you have to be a satellite whose orbit is so radial that it actually plunges through the stellar body of the central galaxy. This is a very strong interaction. So the second requirement is that the minimum distance in units of the size of the halo of the host has to be under 5%. So bringing these two together, here I'm showing you the minimum distance in the orbit in units of the radius of the dark matter halo of the host versus the stellar mass of the satellite divided by the stellar mass of the central. This is all the satellites in the simulation. Our 7 galaxies are below the 5% line. And they have a really small range of mass ratios, around 1 to 1,000. If we look at the observations, this is what the mass ratios are. We don't have any information about how far the real observed galaxies went relative to their host, because you would need to go back in time to know that, but at least we know that we get the mass ratios right. So it seems like in order to be dark matter deficient, you have to be in a very specific regime in this parameter space. If your mass ratio is if the galaxies are very similar, or if the mass ratio is such that they're very discrepant, you won't make these galaxies. What happens here when you have, like, for example, 1 to 1 or 1 to 10, is that they merge very quickly. And what happens down here, if you have like 1 to 100,000, is that the little one gets destroyed. It gets completely stripped apart, and it doesn't survive until today. So there seems to be a sweet spot where you can plunge through and still survive, and then you end up being a dark matter deficient galaxy. Another piece of information I'm showing you are these numbers here, like this 2, this 4, this 10. This indicates how many pericentric passages the galaxy has. On average, these ones have between 1 and 3, and most of these have a lot of those really close interactions. So for example, this is BERT. It has 10 passages, so it has a really weird orbit. And this is blue. No, this is BERT, and this has 14. So just to summarize, there have been 2 dark matter deficient galaxies discovered in the real universe. We discovered 7 in our simulation. We named them after the 7 Cherokee tribes. And to become a dark matter deficient galaxy, you have to be a satellite. Your satellite to central stellar mass ratio has to be about 1 to 1,000. And you have to come within 5% of the radius of the host halo. So it has to be a very strong interaction. And something we notice is that some of these have a lot of passages. They interact over and over again with the host, and they still survive by today. So these galaxies really resonate with me because although I'm not Cherokee, I have indigenous ancestry, and I think about my indigeneity and how I interact with the United States and with Mexico and Canada and with any colonial power. And for me, it's thinking about my ancestry, it can be very painful to realize that, well, that they took away our language or our customs or our cuisine. It's really weird for me that I have a European name and I look at myself in the mirror and it's really strange, right? But in the end, they didn't take away our core. This colonization process didn't destroy us. We're still here and our core is still intact. So that's why these galaxies really resonate with me. So thank you so much for your invitation, and any final questions.
Thank you very much. That was a great presentation. There are definitely some more questions. Are there questions in the audience here? Because I keep neglecting you guys. So we'll go to the Q&A here online. So there's a question: why does DF4 have such a large error bar in the bottom figure that you showed before?
So
for one of the earlier figures, I think.
So maybe it was this one. Is it this one?
Could be, probably.
So in the X direction or the Y direction?
Question didn't say. Maybe she can elaborate, but.
Well, I guess in the X direction, because it's very hard to measure stellar masses for such faint objects. In the y direction, it's you have to make a lot of assumptions to actually say how much dark matter you have. So we decided to report it as upper limits.
All right, another question. Should we see more massive dark matter deficient galaxies in galaxy clusters?
So let's see. So it seems like it's not the mass of the dark matter halo that matters, but the mass of the stellar mass of the central galaxy. So if galaxy clusters have galaxies like that, and you can meet this 1 to 1,000 ratio there, then we should be able to find them. And in the paper, we make a recommendation. We expect galaxies that have at least 10 to the 11 solar masses should have at least one satellite that is dark matter deficient. It's an invitation to observers to look for them.
Okay, another question here. Is dark matter distributed uniformly throughout the halo? Is it really a halo? That is there really no dark matter at the center?
So dark matter is not distributed uniformly. It's there is a radial profile, and in general it tends to be very centrally concentrated. So yeah, I guess if you think of halo as something that only lives externally, then maybe it's a misnomer, because the simulations show that you should have dark matter in the center.
All right, there's more questions. Might your research make it possible to create targeted approaches to finding more dark matter deficient galaxies?
So yes, and so making the prediction of where you're likely to find them is one of them. For example, we find that they orbit very specific stellar masses. We also make the prediction that if you're looking at massive galaxies, 15% of the satellites should be dark matter deficient. So I guess if you look at things like the Milky Way or the local group, or you look at around galaxies that are low, like intermediate mass, like Andromeda or Milky Way, our simulations tell you that you shouldn't find any. That you're looking in the wrong place. You have to focus on very massive galaxies.
Right. Can you talk a little more about the process that went into picking out these galaxies? There must be millions in Firebox, and I imagine doing a halo finder-like process would be difficult with how diffuse they can be.
So because I constrained myself to low mass galaxies, that brought the numbers down a little bit. And what I did is I was making images of every massive galaxy and looking at the satellites. And this is what happened. So when people do simulations like this one, they have automated algorithms that basically find what particles are closer to other particles and what particles are bound, and then you can select galaxies, right? I noticed that my algorithm didn't pick up any of these 7. It missed them. So it turns out that maybe sometimes the eye does a better job than these algorithms. And it could be the case that other simulations that have not found this, maybe it's because their automated algorithms are not working. But of course, the bigger the simulation, the harder it is to look at one by one by one. So this was a very tedious process, and I had a notebook where I was taking notes for each system to make sure that I had all of them.
All right. Can we say then that there appears to be a mechanism that removes dark matter from a satellite galaxy?
So the mechanism is tidal stripping. So what happens is when these galaxies first became satellites, they were like 30 times more massive. They were dark matter dominated and they were gas rich. Now, the first thing that goes is gas. And the reason is because the host halo has gas too. So there is this hydrodynamic interaction between the gas of the satellite and the gas of the central. That's called ram pressure stripping. So the gas is the first thing that goes. But then because you have gravity, you have gravitational tides, that it strips away the stars and the gas. I'm sorry, the stars and dark matter. But you might ask, well, why does it strip away the dark matter preferentially over the stars, right? And what we think is the following. So when you make stars, you need really cold dense gas, which is at the bottom of the potential well. So you make those stars, and those stars are strongly bound. But the dark matter is more loosely bound. It's in a more elongated orbits. So when it becomes a satellite, it's easier to strip away the dark matter than the stars. And that's why we believe that this happens. It's something we need to check. So paper 2 will be about that.
Great. Are there any more questions, either in the audience here or online? Looks like not. So, so thank you again. That was really a wonderful talk and really a model of how to give an accessible talk. So thank you very much, both for the content and the form. It was really lovely.
Thank you. It was my pleasure.